Yeah, hi everyone, and thank you for joining me. Now, before I start talking about deep learning and fuzzy logic, I want to ask you if you've ever heard of fuzzy logic before. Just raise your arm if you have, or maybe just a few people. Okay, that's what I kind of expected. So I'm going to give you a quick introduction about what fuzzy logic actually is. Fuzzy logic deals with statements of partial truth, and this way we can imitate natural language and human reasoning. So what do I mean by that? You already see this question, is it hot? And now in natural language, we don't have a definite yes or no. We usually answer with some kind of vague answer. We might say, oh, it's moderately hot, so it's not really a yes or a no. So binary logic cannot deal with that. We only have zeros and ones. And with fuzzy logic, we can translate these unsure words or linguistic values into something a computer can deal with, and then make decisions based on ranges of data instead of one discrete data point. And fuzzy logic is usually part of a system. We have 3 steps. There's first the fuzzification part, then the fuzzy inference, and the defuzzification. The fuzzification part is something like I've talked about before in the sentence, is it hot? So we have an input variable from the real world, maybe a temperature or the speed of a car, and we want to transform it into a fuzzy value. We have a discrete input, a crisp input, and we want to put a word to it, a linguistic value. And this is what the fuzzification does. I'm going to get into it later on. And with these values, we have created words we can use for a fuzzy inference. This is our rule base. It helps us to define fuzzy rules, which are close to natural language in the form of if and then. So, as we would say in the real world, if it's hot, then the ceiling fan should turn at a faster speed, for example. This is pretty vague. A computer cannot work with that. But the fuzzy values we put behind it help us come to a conclusion. And the fuzzy inference also gives us an output which is still fuzzy. And in the last step of the defuzzification, we want to then calculate a value which we can work with. And depending on the area in which we apply a fuzzy logic system, this can be, for example, in electronics, we want to calculate how fast the ceiling fan should rotate. And we say if it's really hot, it should rotate faster. And we want to translate it into a real number the system can work with. Or in aerospace, if we want to calculate the altitude of a spacecraft. But fuzzy logic has also found its way into natural language processing. And I'm going to show you an example to really give you an idea how fuzzy logic works with all its calculations. So what you can see here is actually the configuration view of BSI, of our BSI tool, but I'm going to show you this as an example of just how it might look like to use fuzzy logic. So we might have a use case where we want to classify how political a text is on a scale from 0 to 100 based on the appearance of certain words. So how many times does a certain word appear? And based on that, we want to say how political a text is. This is a really simple example, just to get you into how all of this works. So we get a real input number, maybe the appearance of the word Bundestag, and we want to say, does it appear often, or pretty rare, or moderately? And these are already linguistic values which are kind of fuzzy, and we want to decide how much does our input value, so the appearance of a certain word, belong to a word, to a linguistic value, for example, pretty often, or moderately, or pretty rare. And for this, we define membership functions. A membership function translates our input value into a degree of truth. And as you can see in the right part of the configuration, this function looks like a triangle, and it's defined by a set of points. So we say if we have a word count of 25, then this word count definitely belongs to the word moderately. So we say it's moderate. And we get ranges from 0 to 1. And depending on the input number, we get different degrees of truth. And at the end, we have a vector containing of all our linguistic values and with the calculated degree of truth for every word we have. Now that we have these linguistic values, we can then define a rule base. And the rule base is pretty close to natural language. So we might say, if a certain word appears a great number of times, then the text might be political. And the rule has its if part, which is the premise, and it has the then part, which is the conclusion or the consequence. And unlike to binary logic, we don't have a 0 or 1 for a rule. So we don't have an activation or no activation, but we have a degree of which the rule fires. And each rule gives us an idea of how we classify a text or the politicalness of a text. These are still pretty vague values. These are our linguistic values. And to calculate the degree of activation, we have different methods, which you can see on the right. To calculate the conclusion of a rule with only a single input in the premise, it's pretty simple. Then we have just exactly the value we have as an input. So if we have the appearance of the word Bundestag is rare, if we have a value of 0.5 for this, then the activation of the rule is also 0.5. Now, if we use logical operators like and or, there are different methods to combine these values. And they are called T-norm or T-conorm. It's a conjunction of logical operators with fuzzy values. And I'm not going to get too deep into this, but there are minimum and maximum conorms or T-norms, which just say if we use an and, we use the minimum value in the premise, just like in the binary logic, right? If we have a 0 and a 1 and we use an and operator, we get the 0. And here we just get the minimum value. And for the or logical operator, we use the maximum value. We can also use product calculation, so we use the product if we have an AND operator, but mostly it's just the minimum and the maximum operators. Now, if we have rules defined for the same output value, we have, for example, 2 rules for moderately political, then we need to decide how we combine these activation degrees. And here we have different methods we can choose from. Right now, the sum value is selected, but the average value is also possible. So we combine all these rules and calculate, for example, the average value. And this is going to be our output. So we have, again, an output of vague words, which we then want to put into a crisp output number again. For this, we have the defuzzification step. Now, this looks a little complicated, but essentially it's like the fuzzification. We have our membership functions, and we want to now do the different, like the other way around of calculating. So we don't want to get a fuzzy value, but we want to get a crisp value. And we have here our results from our fuzzy rule base. These are all values in the range from 0 to 1. And now we want to put these values to our degrees of membership, so our membership functions, and draw a line exactly where our value lies. And right under this cut, we want to decide the area. And this is where the complicated part comes in, because we want to decide the center of gravity and then find out on which scale we lie here. So if our center of mass lies somewhere here, because we have moderately political or barely political, then we also get a low number on our scale. And we have 2 different methods to calculate such a value. Also, I'm not going to get too deep into that because this is too theoretical, but we have the center of gravity, which looks at the outlining shape of these multiple areas and then decides where the center of mass lies. Or we can look at the single areas and see their overlapping parts, and this way we can give more weight to certain areas. and then we calculate the center of mass. But yeah, this is not always used in the use cases we have at BSI, so I'm not going to get into this. But let's talk about how we combined deep learning and symbolic AI, or why we did it. In a critical paper, Gary Marcus said that the right move today may be to integrate deep learning, which excels at perceptual classification, with symbolic systems, which excel at inference and abstraction. So what does he mean by that? Deep learning usually depends on large numbers of data, training data, test data, and also on good data. And in the real world, this is not always the case. There's always a limit to the training or test data we have. And this has a big influence on how well the accuracy of deep learning models is. And now the symbolic AI doesn't really need that much of data. It can deal with less through inference and abstraction. So the idea is to actually combine these two and get a better classification. And this is what we did at BSI. We have the following use case, where we get a customer rating for customer support, for example, and we want to classify this text. We want to find out what topics are discussed, and are they discussed in a negative way or rated in a negative way, or are they rated in a positive way. The possible topics are, for example, speed, competence, customer orientation, and so on. And we want to find out the top 3 mentioned topics that I mentioned positively or that I mentioned negatively. And behind all of this classification lies this. And our problem was at first that we have different bird classifiers which are trained on different sets of data, and each model has a different reliance or accuracy. And we want to balance that out by using fuzzy logic. Now, this whole thing is a configuration of a so-called brain, which we use to solve the classification problem. This brain contains multiple blocks like these, and they each have their own task. For example, these orange ones. I'm going to zoom into this. These are our ONNX runtime cortexes. These are building blocks that contain the BERT classifier, the trained models in an open source ONNX format. And they give us a confidence about each topic and the sentiment for each topic, so if it's negative or positive. And these confidences are then used in the fuzzy logic part, which is this. We have the fuzzification step, the fuzzy inference, and the defuzzification, which I've already talked about. And now we're going to look into how a membership function looks like in this use case. So what we get as an input is not an appearance of words, like in the example before, but we have a confidence of a model. So we have, for example, a model for the competence topic, and our model says, for example, that it has a confidence of 0.6 that it's about this topic. And now, by looking at metrics like a confusion matrix or the precision recall curve, we figured out what's the best way to trust this confidence. So we have 2 fuzzy values. We have a fuzzy value for high confidence, and we have a fuzzy value for moderate confidence. And we have found out that starting from 0.6, for example, we can trust this confidence that it's exactly about this topic. And for different BERT classifiers, for different topics, these membership functions may vary. So this way we can balance out the differences between the BERT classifiers. Now that we have our fuzzy values, we can now create a rule base. And this rule base is pretty simple. We have just rules that say, okay, if it's about this topic and if it's a negative mention of this topic, then we have the category negative topic or negative competence, for example. And as we have already said, the AND operator combines these 2 fuzzy values, And for example, if we are not pretty sure if it's even the topic, price and product, this value can have an influence in the rule on the sentiment. So this way we can decide if it's actually about this topic and its sentiment. Now in the last part, this is not really necessary, but if we want to, we can transform these values again into maybe a rating. Maybe we want to have a range of negative 0.5 to 1.5 to classify how this topic is mentioned. Maybe we want to say 0, negative 0.5 is the lowest rating we can get, and 1.5 is the best. And we do this for every topic we have, and for the inputs we have from our rule base. And then we can, again, use a defuzzification method to find out on what scale we lie here on the x-axis. By using fuzzy logic, we have actually created something that can easily be extended. Now, this can be, for example, by adding new fuzzy variables. We cannot only use the confidences of the BERT classifiers. We may want to look at different attributes and want to add them to our fuzzy variables. Or we can extend our fuzzy rule base by adding more rules. Maybe we have found out that if a certain topic is mentioned, it's usually also the other one, so we can combine these different confidences or fuzzy variables and create new rules to then have a better classification. And the good thing about this is that each step of the fuzzification process is independent from another. So if I change something about a membership function, I usually don't have to change anything about the rule base, because the rule base has its words which it can work with, and what lies behind this is not really important for the rule base. We just define our linguistic rules and don't worry about what is going on before or after that. And this point of having natural language in a fuzzy rule base is actually great for people who are not really into machine learning. So when we use our tool, our BSI AI tool, we have this advantage of showing people who have no idea about machine learning what to do, because they might say, oh yeah, of course, if it's this topic and maybe it's also this topic, then we can say it's this conclusion. So they have their expert knowledge and they can formulate their rules in the natural language and don't have to know anything about membership functions or anything else. And this is my talk about combining deep learning and fuzzy logic. Thank you.
So, questions?
Yeah. Well, first of all, thank you very much for your talk. And my question is about your customers. Like, what kind of customers are you now working with? Mm-hmm. And where do you see your technology? Like, where could it be employed next? Like, for example, I didn't understand everything, but of course. But like, I could imagine this being used in like some social media filters, for example, if like a text is way too political or things like that. Are you going in that kind of direction, or like what's your imagination with your product?
So our customers at BSI are other businesses. They are from retail or insurance and companies like this. And usually the use case is, for example, the customer rating, but we also have cases where we want to classify emails, for example. We get emails and we want to know which team we should put it to for further answering of the email. And there are different topics which email can belong to, or category. And with fuzzy logic, you can also regulate that. So what we have found out, we have already a use case with fuzzy logic and email classification, combined also with bird classifiers. And there we found out that usually a few categories get mixed up. They're pretty close, and our bird classifiers always mix them up. And with our fuzzy rule base, we could kind of regulate that. This is some kind of use case we have right now.
Okay, thank you very much.
Thanks. I have a question about scalability. So I see two concurring aspects. On the one hand, it seems like you need manual input to like select the scales, but then on the other hand, without the end-to-end training, you don't need to retrain if you want to add categories. So how does this balance out? Is it like, does this allow for quicker development, or is that more work because there's more manual work?
Do you mean adding in the fuzzy logic part and using it? Yeah, so going back to the email use case, we actually have found out, we worked with the confidences of the bird classifiers, but we also figured out we can use customer data information, because we have a customer relationship management product where we can go to all of our customer data and maybe look for attributes there that are interesting for further classification and use it. Now, of course, it's work to get these attributes and to put membership functions to it and to kind of decide how we want to transform it. But there's also a possibility, which we have not explored yet, to automate this. So we can also learn what the membership function should look like, or learn what the rule base should look like automated learning.
Thanks.
So, more questions? Thank you very much.
Thank you.